Have you ever wondered how far the water behind the Hoover Dam will eject from an outlet? Will the water follow the trajectory of A, B, or C? This is a similar problem that Evangelista Torricelli answered back in 1642. Evangelista Torricelli was an Italian physicist and mathematician who lived in the first half of the 17th century. He is best known for his contribution in the mercury barometer and of course the famous Torricelli's law, which relates the velocity of water to the height as V equals the square root of 2gh. Torricelli's law is a special case of Bernoulli's equation, which is a result of the conservation of mechanical energy for ideal flows. The mechanical energy includes pressure, kinetic energy, which is 1/2 rho v squared, and potential energy, rho gh. For the discharge problem, the pressures at the 2 points are the same as the atmospheric pressure, and the velocity at location 1 is almost 0. If we chose the origin at location 2, then h2 is 0. The result becomes Torricelli's law, which is velocity equals the square root of 2gh. In this video, we will use 2 experiments to test Torricelli's law. The first experiment involves a horizontal flow of water out of the main reservoir. In this experiment, we will observe the flow of water decreasing as the height of the water decreases from the reservoir. The height of the water from the hole is h, and we measure the horizontal distance the water traveled as the experimental data. The experimental distance is labeled in red, while the ideal distance is labeled blue. This image was taken at a later time. As you can see, the horizontal distance has decreased as the height of the water is lowered. The graph is a summary of the horizontal flow experiment. The horizontal axis is the height of the water from the hole, and the vertical axis is the differences between our data and a theoretical prediction from Torricelli's law. The second experiment will use tubes to point the exit flow into a diagonal position beside the main reservoir. Theoretically, the vertical distance of the water coming out of the spout is h times the square of cosine theta, where theta is the angle of the spout relative to the vertical axis. Similar to the first experiment, we measure the height of the water from the hole as h and use the vertical distance the water traveled for the experimental data. The experimental distance is labeled in red and the ideal distance is labeled blue. This image is taken at a later time. As you can see, the vertical distance decreases as the height of the water is lowered. The graph is a summary of the diagonal flow experiment. The horizontal axis is the height of the water from the hole, and the vertical axis is the differences between our data and the theoretical prediction from Torricelli's law. Now going back to the original question of how far the water will eject from the outlet of the Hoover Dam, we calculated the theoretical distance to be approximately 170 meters. From this image, we estimated the actual distance to be about 124 meters. This gives an error of 31%, which is very close to the data of both our experiments. That concludes our presentation over Torricelli's law. Thanks for watching.
Australia, the toilets don't flush, by the way?
Yeah.
You sure?
Yes.
There's some people
Why
that
would
do
somebody
the
make that up?
experiment.
Because it sounds cool. And they wanted something to put on their blog that people would reblog.
I think that rumor's been around before blogs.
It's not true.
This is the audio track for the back of our smooth jazz elevator music.
That's your
No, we should
Chicago?
find some big epic.
Oh yeah, that's the definition of Chicago.
Evangelista Torricelli is an Italian Oh shoot.
So we have to bring that velocity equals the square root of 2gh to their brain.